PANS-OPS is a rigid mathematical architecture. It exists so pilots flying through blinding weather can rely on superior procedural design to avoid terrain, rather than needing superior stick and rudder skill to survive it. I am Captain Pankaj Pahil, and this is your masterclass on ICAO Document 8168. The document is strictly divided. Procedure designers use Volume 2, while flight crew requirements are within Volume 1. PANS-OPS relies on three baseline assumptions: all engines operating, an altitude of 600 meters MSL, and ISA plus 15 degrees Celsius. Engine out contingencies and the resulting obstacle clearance calculations are the legal responsibility of the operator. PANS-OPS parameters assume all systems are functioning normally to ensure standard obstacle clearance. This structural timeline maps the entire sequence of a flight. We will track the specific regulations governing departures, map the en route altimetry and holding procedures, and conclude with the descent through the approach segments. Every parameter in Document 8168 defines a physical boundary in space. Understanding this geometry allows a pilot to verify the safety of a procedure, rather than just following an instrument needle. Looking at this cross-section of a departure segment, the airspace is symmetrically divided. The inner half of the total width forms the primary area, where full minimum obstacle clearance, or MOC, is applied. The outer quarters form the secondary areas, where clearance tapers down to zero at the absolute edges. However, if an aircraft executes a turn without track guidance, that tapering safety buffer is eliminated. The entire width of the airway must be treated as the primary area, demanding full obstacle clearance across the board. The required MOC values are mathematically fixed. At the departure end of the runway, the clearance requirement is 0 meters. It then increases at a rate of 0.8% of horizontal distance flown. If a turn is required, the turn initiation area enforces a strict minimum clearance of 90 meters or 295 feet. This 3D wedge diagram illustrates the procedure design gradient. It starts with an obstacle identification surface rising at a 2.5% slope. PANS-OPS then layers an inflexible 0.8% safety margin on top of that terrain. Combine them, and you get the standard required climb gradient of 3.3%. While fixed-wing aircraft adhere to that 3.3% standard, Category H helicopters operate under tighter tolerances and must meet a steeper procedure design gradient of 5%. Obstacles measuring 60 meters or less in height are categorized as close-in. These do not alter the published climb gradient. Designers publish a note to ensure the pilot is aware of their proximity. The procedure design gradient is a non-negotiable geometric wedge. Match or exceed it, and you will outclimb the terrain ahead. For a standard instrument departure, the spatial rules constrain lateral movement. For fixed-wing aircraft, turns are prohibited before passing the departure end of the runway, and they cannot be initiated below an altitude of 120 meters above aerodrome elevation. To maintain consistency across airspaces, procedure designers normally optimize these first turns to happen at exactly 600 meters from the beginning of the runway. This layout maps out the four architectural options when no track guidance exists, known as omnidirectional departures. In the standard case, if the terrain permits, the aircraft climbs straight to that critical 120-meter mark before turning in any direction. If obstacles penetrate that standard flight path, designers deploy constraints. They will either dictate a specified turn altitude, forcing a straight climb to a much higher vertical point before maneuvering, or they will authorize a sector departure, restricting your turn strictly to safe headings. If ATC offers radar vectors during departure, you must refuse them unless you are already above the minimum altitude required for engine failure clearance, or if the route is explicitly non-critical for terrain.
Whether tracking a highly defined SID or climbing blindly into an omnidirectional zone, the math enforces rigid altitude floors. Lateral maneuvering is blocked until vertical safety is achieved. This diagram shows the vertical boundary separating local pressure settings from standard atmospheric pressure, the transition layer. The altimeter toggle is precise. Climbing through the transition altitude, you switch your altimeter to 1013.25 hectopascals to fly flight levels. Descending through the transition level, you switch back to the local QNH to read actual altitude above sea level. The vertical position of an aircraft descending through the transition layer is expressed exclusively as altitude to maintain vertical separation from local terrain. Moving to this radar diagram, we see the geometry of holding procedures. Based on your heading, you must execute either a parallel, offset, or direct entry into the hold, with a 5-degree zone of flexibility on the sector boundaries. Inside the hold, outbound timing is capped at 1.0 minute at or below flight level 140, expanding to 1.5 minutes above it. Speeds are similarly capped to contain the turn radius. For Category C, D, and E aircraft, maximum normal speed below 14,000 feet is strictly 230 knots, and the rate of those turns is an absolute rule. You must turn at 3 degrees per second or at a bank angle of 25 degrees, whichever requires the lesser bank. Holding procedures function as geographically confined racetracks. Every timing limit and speed restriction is engineered to keep the aircraft contained within protected, obstacle-free airspace. For SSR operations, if you have a serviceable Mode C transponder, operate it continuously at all times. Without specific ATC direction, operate Mode A on code 2000, and never operate the ident feature unless ATC specifically requests it. The ACAS logic tree details the airborne collision avoidance system.
In the precedence hierarchy, physical threats, like stall warnings and wind shear, always override ACAS commands. Within ACAS, if the system generates a traffic advisory, use it solely for situational awareness. Do not maneuver your aircraft. During an emergency, these procedural hierarchies strip away ambiguity. They enforce a standardized behavioral override to ensure isolated incidents don't escalate into disasters. As the flight concludes, approach procedures are dictated by the speed of the aircraft. Categories A through H are based entirely on VAT, the indicated airspeed at the threshold. This is calculated as the stall speed multiplied by 1.3 in the landing configuration. To safely reach that threshold, a continuous descent final approach, or CDFA, is utilized. If flown with advisory VNAV guidance, it qualifies as a 3D instrument operation. If it relies on manual calculations, it remains a 2D operation. This pipeline graphic illustrates an instrument approach functioning as a funnel. As alignment increases across the arrival, initial, intermediate, and final segments, required obstacle clearance drops sharply, from 300 meters initially, down to 150 meters, and finally to just 75 meters on a non-precision approach. To qualify as a straight-in approach, that final track must align within 30 degrees of the runway centerline, exceed that angle, and terrain dictates a circling approach instead. This chart divides ICAO approach classifications into Type A and Type B operations. Type B encompasses strictly 3D precision approaches, advanced Cat I, II, and III operations, defined by a decision height below 75 meters or 250 feet. Track widths, altitude floors, climb gradients, and containment zones. PANS Ops is the silent mathematical framework keeping you separated from the terrain. Memorize its parameters, respect its margins, and fly with absolute precision. I am Captain Pankaj Pahil. Study hard and fly safe.